3171 for the subarray with bitwise all closest to k. I think this problem is really easy to understand because we are just giving an array nums, but this num is going to be 10 to the power 5, and we are also giving an integer k. And we want to get the minimum possible value of the absolute difference. So the absolute difference just means k minus nums l or nums l plus 1 until nums r. Yeah, so for example, 0 to 1, so index 0 to 1, 1 or 2. So what is 1 or 2? So this is a 1 and this is a 2. 2 is 1, 0. Yeah, so 1 or 2, it is 1, 1. So it's going to be 3. And 3 minus k going to equal to 3. So the absolute value is going to be 0. So this is the minimum value. So we're going to return a 0. Yeah, as we can see, 0 is going to be the minimum absolute value of any integers, right? Yeah, so this means it is possible. So we're going to return the minimum value, which is going to be 0. And we can also check the second case. So for example, nums 1, 1, it's going to be 3, x or 3, it's going to be 3 minus 2, it's going to be 1. So the minimum value is going to be 1. And we cannot find a value which is going to be 0. It is not possible. And for this case, example 3, there's only one value. So we're going to directly choose 1. So 1 x or 1 itself, we're going to just use 1. So 1 minus k is going to be 9. So the absolute value is going to be 9. We're going to return 9. So the obvious idea is that why not just solve it by using brute force. So we're going to prepare the length of the nums, and we just need to use 2 for loops. But this is not possible, but at least we can write a brute force, right? So I to n. So the result is going to be the minimum of the result with the absolute value of, here we're gonna, the XOR, we're gonna use the reduce. Yeah, so for this this kind of coding, I just want to explain why the brute force didn't work. Although this is a O(n) cubic time complexity, but I just wanted to explain why it didn't work. Yeah, so we're gonna use reduce. Here is all, and nums I to j plus 1 minus k. Yeah, so this is going to be the minimum value, and finally we're going to return the result. So we're going to set the result to be infinity. Now let me just run it. Yeah, as you can see, it works. It passed for some testing cases, but it cannot pass for all testing cases, because this is the O(n), this is another O(n), and this is the third O(n). It's going to be O(n) cubic. Yeah, so since O(n) cubic didn't work, O(n) square will not work either. Yeah, because n gonna equal to 10 to the power 5. As you can see, it didn't work. Although we optimize it to O(n), it didn't work. Yeah, because for here, we should know that definitely we can optimize to O(n). So yeah, so here we can yeah, we can optimize to O(n) squared. Definitely it didn't work. Yeah, so this means I will not try to optimize to O(n) squared because it didn't work, even though this is O(n) cubic. This is just to explain what is the meaning of the problem. Yeah, now we're gonna try to change this part a little bit to make the problem easier to solve. Yeah, so actually we do not need to use we still need to use 2 for loops, but the time complexity gonna be n times log u. U gonna be 10 to the power 9. Yeah, u gonna be nums I gonna be this value. So how can we write that? So we're gonna prepare a variable j, and j gonna equal to I minus 1. Yeah. But before that, we're going to use I, because even it is a single number, it might be a possible result. So our result is going to be the minimum of the result with absolute value of nums I minus k. Yeah. Now we're going to prepare a variable j. J is going to be, so for example, if this is a nums I, like 1, 3, 1, 3. So if this is I, j is going to be I minus 1. So this is going to be j. Yeah. j is just used to accumulate the value of, so for example, 1, x or 3. So it's going to be reserved value for here. So 1 or 3, it's going to be 3. So nums j is going to equal to 3. Yeah. J just used to accumulate all the values. So for here, this is I, and for here, it is actually nums j or nums I. Yeah, this is what we are doing, because this can make the problem really easy to solve. This can reduce the time complexity to n log u. Yeah. Now let's just continue. So since j is I minus 1, we're going to check j going to be more than or equal to 0. So here we're going to use the log trick. So what is the log trick? The log trick is that normally if the problem is O(n) square, we're going to reduce the problem to n log u. So this is the log trick. This log u time complexity going to be the log trick. I'm going to explain it later, but let me just finish the coding to explain why we're going to solve it like this. Yeah. So if j is more than and equal to 0, and nums j or nums I not equal to nums j. If it is not equal, we're going to continue to calculate. But if nums j or nums I equal to nums j, we're going to break the while loop. This is because all the calculation has already been calculated. We don't need to go back. Yeah. So for example, this is the array, and this is I. And while we are calculating, we are go back nums something with the nums I until nums j or nums I. And if this value equals to nums j, so this means nums I gonna be a subset of nums j. And from here, this means until to the next value maybe j plus 1. This is the next value to the left. Yeah. So nums j plus 1 gonna still nums I gonna be a subset of nums j plus 1, because this is the OR operation. So this set gonna be bigger and bigger and bigger. Yeah. So this means the nums I doesn't matter. Yeah. So the idea is if the nums I is a subset of the nums j, so nums I gonna still be a subset of nums j plus 1. And this value reserved here because it is nums I or nums j or nums I equals to the value of nums j. We will not continue to calculate it because all the previous value has been calculated before. So this nums I doesn't matter. So we're gonna stop it. Yeah. So this is why we're gonna use nums j or nums I not equal to nums j. Yeah. But I will explain it later why exactly we're gonna use this and why the time complexity is gonna become log u instead of O(n) square. If everything's okay, so j gonna plus minus equal to 1, and nums j gonna accumulate it with the nums I. So this is according to the problem we needed to calculate the range from L to R, and it's gonna be the bitwise OR operation. Yeah. So here we're gonna record the final result. It's gonna be the minimum of the result with absolute value of nums j minus k. Yeah. Now let me just submit it to check if it works, and submit it. Yeah, as you can see, it works and it's pretty fast. Now let's just analyze why we can write it like this. Yeah. So we're going to use the idea. So for example, we have four numbers. So this is the nums array. It is 1, 2, 4, 5. So now we have four numbers. Let's just use A, B, C, D. Yeah. We have four numbers, and according to our algorithm, so we're going to check each of the number from A to D. So this is I. So this is okay. Yeah, so for this number A, we just calculated according to the absolute of the nums I. So absolute of A minus K, and we calculated the value. So for each of the single values like A, B, C, D, we calculated. But we didn't calculate something like AB or ABC or A, B, C, D. I mean the XOR operation. I mean the OR operation. Yeah. So now what are we gonna do? So for this A, it is okay, but what about this AB? So for while we are checking this B, so this B is okay, so we're gonna put it here. And what about this A? So this A at this position, because if it is not equal, so for example, if the previous value nums J, it is A, or nums I, it is B, A or B, if A or B, so if A or B not equal to B, yeah, so we're going to continue to calculate. If it is not equal, so here gonna be A or B. Yeah. Now for the next loop, so if I equal to C, if nums I equal to C, so here we're gonna keep it. This is a C, and here gonna be, if they are not equal, so here gonna be BC, and here gonna be A or B or C. Yeah. If they are not equal, we're going to continue to calculate. Yeah. So here is D, and here is C or D, and here is B, C, D. Yeah. And what about here is A, B, C, and D. Yeah. So this is for if they are not equal, we're going to continue to calculate it like that. As we can see, the time complexity is going to be like O in cubic. Definitely it didn't work. Actually, we don't need to calculate all of them. So just imagine from some places. So what if this C or D equals to this C? So currently here is a D. If this C or D equals to C, is that possible? So let's just imagine it is possible, but we don't know how many calculations we're gonna make it possible. Is that will be 10 to the power of 5, or it's gonna be just like 30 calculations? Basically, it's gonna be log 10 to the power of 5, log 10 to the power of 9. It's gonna be just 30 calculations, and then we can find it. Oh, this is nums J or nums I equals to nums J. So here, let's just imagine if this is C or D equals to C. Yeah, let's just imagine if it is possible. Yeah. So now C or D equals to C. So this means D will be a subset of C. Yeah, let's just understand the numbers as a boundary set. Yeah. So so currently this D gonna be a subset of C. Yeah, because they are equal. C or D are equal to C. Now, what are we going to continue to calculate? Because C or D equals to C, so here, this is a B or C or D, but C or D equal to C, this means we can write here as BC. So here gonna be BC, and here C or D gonna be ABC. Yeah. Now what happens is that this is a BC, and this is also BC. This is ABC, and this is also ABC. This means all the previous calculation, for example, this BC has already been calculated before, because this BC gonna minus K, it has already been calculated. And this ABC minus K, it has already been calculated. So why not, if some numbers is calculated, why not we're gonna continue to calculate the same result? Because that is not necessary, so we don't need to repeat all the calculations after that. Yeah, so this means if C equals to C or D, we will stop it. We'll stop the while loop, but we will not continue to calculate. Yeah, so by this way, we're going to reduce the time complexity. Now let's just prove that. Is it possible to make C equal to C or D? Is that possible? Yes, it is. Let's just use an example. Yeah. So is that possible, C equal to C or D? Yes, it is. So let's just try to use some examples. Yeah. So in our set, let's just use a set to represent binary numbers. So for example, we have, let's just use maybe binary numbers. Let's just use the binary numbers. Yeah. Yeah. If we have some binary numbers like 1, 1, maybe 0, 1. So this is a binary number, and then we're going to continue to do the XOR operation. Yeah. So if some value, so for example 1 0, or this number not equal to this number, yeah, so 1 0 maybe 0 0 0, so the result gonna be 1 1 1 1 1, yeah, because if they are not equal, so definitely, yeah, because if this number is not a subset, yeah, I mean if this number is not a subset of this number, basically this is a set, the binary number is a set, yeah. So if this is a nums j, yeah, let's just use this is a nums j, yeah, how can I explain it? Let me, so this is a nums I, so this is a nums I, yeah, so this is 1 1 1 0 1, this is nums I, and this is a nums j, yeah. So currently if nums j or nums I not equal to nums j, so definitely it is not equal, because the final result is going to be 1 1 1 1 1, it's not equal to nums j. So this currently this value is going to be nums j, yeah, it's going to be 1 1 1 1 1. So what's going to be the next possible number? Yeah, if our binary number is only with a 5 bit, so maybe the next number is something like 0 0 1 1 1. So what happens for this one? For this one, so this is a nums j, and this is our next nums I. So this nums I or nums j gonna equal to nums j, because 0 0 1 1 1 or 1 1 1 1 1, the final result gonna be 1 1 1 1 1. Definitely it is equal. So we're gonna stop the while loop. Yeah. So how many such kind of calculations maximum? It's gonna be like 30 calculations. It's gonna be log 10 to the power 9. Why? Yeah, because for the first time maybe for the binary number we have a 1, for the next time we have a 1 1, and for the next time we have 3 ones, until we have 30 ones. So until we have 30 ones, so it's going to be 30 such kind of calculations. Otherwise, if something this is 1 1, next is 1 next is 1 0, so we're gonna stop the while loop, because it's gonna meet the conditions. Yeah, so maximally it's going to be 30 such kind of calculations. So this kind of calculations is going to be on 30, and this is ON. So this is why the time complexity is n log u. Yeah, this log u basically equals to 30. I think that's all about it. And thanks for watching. See you next time.